All right, last lesson of the semester. Um, it it's nice. We don't always have time in the semester to talk about probability. And it's nice when we get a chance because um, it unfortunately in the high school curriculum that you don't see a lot of probability. You don't see much counting, and it is an important idea. And it's also nice because you think in a different way to do these kinds of problems. So it's a little different way of thinking than the algebraic kind of methods that we've been using. All right. So when we're talking about probability, we're going to talk about experiments. Experiment is just something you do. It could be drawing a card from a deck. It could be rolling a die. They call those experiments. And then what happens when you do the experiment is the outcome. And the outcomes that we're interested in we call events. So a little bit of vocabulary there. In general, probability. The way we're going to calculate it is the favorable outcomes over the total possible outcomes. I think of favorable over total. So this is where our counting comes in, because we're going to need to count the favorable outcomes, and we're going to have to count the total outcomes. And sometimes that can get a little bit tricky. Probability is going to be a fraction or a decimal between 0 and 1. And this includes 0 and 1. So it's 0 and 1 inclusive. And if our probability is 0, what does that tell us? If the probability of something is 0. It's not going to happen. It's impossible. And a probability of 1. What does that tell us? It's certain. It has to happen. And just one more piece of vocabulary. All the possible outcomes is called the sample space. So just if you see that term in the homework, they're just talking about all the possible outcomes. All right, so pretty easy idea, favorable outcomes over total outcomes. So what I want to do is go through some examples, because figuring out the number of favorable outcomes and total outcomes depending on the experiment, depending on what you're talking about, can be kind of difficult. So let's start off with some easy ones. So we have a standard deck of cards, 52 cards. And we're going to, for these next two, we're going to draw a single card. So for our first example, we want the probability of drawing a king. And the way we write this, we write P of king. Probability of king. Well, for our deck of cards, how many total outcomes are there? How many ways can we draw a single card? 52. And how many kings are there? 4. So 4 out of 52, which is 1 out of 13. So we have a 1 in 13 chance of drawing a king. How about the probability of drawing a club? How many clubs are there? 13. And that's 1/4. We could also think of that one as we know that a deck of cards is split into 4 suits, and a club is one of them, so 1 in 4. All right, so nice, easy probabilities to calculate there. Next, we're going to roll 2 6-sided dice. It's kind of interesting in our new geometry books. They've decided that apparently they don't refer to them as dice. That I guess they think that encourages gambling, so they always refer to them as number cubes. You roll number cubes. Two standard dice. So these are your regular 6-sided dice. For you gamers, you D&D people, those would be D6s. Everybody, my son plays D&D, so they talk about D6s and D20s, those kinds of things. All right, we're rolling 2 dice. We want a probability that we get a total of 4. All right, so we're going to say probability of 4. So we're rolling 2 dice. How many possible ways can 2 dice come up? Well, the first one can come up 6 ways. The second one can come up 6 ways. So our fundamental counting principle tells us we multiply. So they can come up 36 different ways. And then we want to know the probability of a total of 4, so we need to count how many ways we can get a 4. Well, let's just make a list here. How many ways can we get a 4 on two die? 2 and 2, 3 and 1, or 1 and 3. So we get 3. And we can reduce that to 1 in 12. So we have a 1 in 12 chance of rolling a 4. How about the probability of rolling less than 4? So slightly different counting. So we know it's going to be something over 36. How many ways can we get a less than 4? 1 and 1, 2 and 1, or 1 and 2. So we get 1 in 12 chance of rolling less than 4 also. All right, let's make it a little more interesting. So now we're going to go back to our committee idea. And we're going to tie in what we talked about with permutations and combinations. We want a committee of 3 from 4 boys and 5 girls. And we want the probability it's all boys. So we pick this committee at random, and we want the probability that when we pick that committee at random, it's all boys. So I'm going to say the probability of boys. So based on what we said last time, how many ways can we pick a committee of 3 from 4 boys and 5 girls? How would we calculate that? We're picking 3 things out of a group of 9. Does order matter here? No, order doesn't matter because it doesn't say president, vice president, secretary, anything like that. It's just a committee of 3. So that's going to be 9C3. That's how many possible ways we could pick a committee of 3 out of 9 people. And for our favorable outcomes, we want all of them to be boys. So we need to count the total number of ways we could get 3 boys out of a group of 4. Does order matter there? No, it's just 3 boys. So our numerator is going to be 4C3. So we can pick the three boys out of 4 in 4C3 ways. We can pick 3 people out of all of them in 9 choose 3 ways. And we calculate that out. That's going to be 4 over 81, which is 1 over 21. So 1 in 21 chance of getting all boys on this committee. Not a great chance, but it's not super small. All right, let's make it one step more interesting. So we're drawing from a regular deck of cards, we're drawing a hand of 5. So like a poker hand, I guess. So we were drawing 5 cards. We want the probability of exactly one pair of 2s. I was telling my other class in one of the courses that I took in my graduate program, there was we did a little unit on probability, and there was one problem in one homework assignment that was calculate the probability of all the poker hands. That was a lot of work. It is a lot of work. All right, so we're going to say probability of one pair. It could be a pair of pretty much anything. One pair of 2s. All right. So out of a deck of cards, how many ways can we pick 5 cards? We're picking 5 things out of a group of 52. So that's going to be 52 C5. That's our total number of outcomes. That's the total number of ways we could choose 5 cards out of the deck. All right, so we're interested in a pair of 2s. Well, how many 2s are in the deck? 4, right? And we're picking 2 of them. So how many ways can we pick 2 things out of a group of 4? 4C2. But for each one of those possibilities, we have the different arrangements of the 3 other cards that are not 2s that can go with the 2 2s. So just like if we had 5 shirts and 10 pairs of pants, the total number of outfits that we could get with those 2, we have to multiply. So after we pick our 2 2s, and we're not picking any more 2s, how many cards do we have left to pick from? We don't want to pick any of these 4 because we have exactly 1 pair of 2s. So how many cards do we have left? 48. And how many cards are we picking out of those 48 cards that are not 2? 3. So we'd have to calculate 4C2 times 48C3 divided by 52C5. And I didn't calculate this out, so I don't have the number here. But that's how we would calculate that probability. So the counting can get kind of complicated very quickly. All right, questions there? All right, so this is get us started on basic probability, but there's some other stuff that we have to take into consideration when we're working on probability. And one of those things is called, we want to be able to combine, we don't just want a single event, we want to be able to combine several events. We're rolling dice and we're drawing cards. We're picking a ball from an urn and we're rolling a dice. We want to be able to combine probabilities. So one of the ways that we do that we need to take into account mutually exclusive events. Mutually exclusive events mean they cannot happen at the same time. So that would be, for example, you can't roll a 2 and a 6 on one die at the same time. You can only get it one way. So those events would be mutually exclusive. And when we're calculating the probability, so we have, I'm going to say we have event A and event B are mutually exclusive. They can happen at the same time. We're interested in the probability of one or the other happening, A or B. And this is written. It's fine. I think it's fine to write probability of A or B. If we use mathematical symbols, the way that you'll see it written is the probability of A union B. For mutually exclusive events, the probability of A union B is the probability of A plus the probability of B. We just add the two probabilities together. And the way I think of it is, if we have an OR probability of this or that, it's addition. Or probability is addition. But sometimes you have events that overlap in some places. They share outcomes. So those we call overlapping events. And an example of an overlapping event is, say you want to find the probability of drawing a king or a heart. Well, some kings are hearts, so those two overlap a little bit. We write the probability of the overlapping events is probability of A intersect B. This is where they overlap. So where the two things overlap. So we have to find the probability of that. The probability of overlapping events. Probability of A union B if A and B overlap. Is, I'm going to write it this way, A union B, is we add the two together, probability of A plus the probability of B, but this counts some of the overlap, and that counts some of the overlap, so we have to subtract the probability of the overlap, A intersect B. So we subtract the probability of the overlapping events. All right, so let's look at a couple of examples using mutually exclusive events and overlapping events. Let's say we have, we're drawing a single card. And we want want to know the probability of a club or a face card. So this is an or probability, but we have to make sure whether or not we have an overlap. Are some face cards club cards? Or some clubs face cards? Yes. So we have an overlap. So these are overlapping events. So we need to calculate 3 probabilities. So let's calculate the probability that we draw a club. Well, how many didn't we already do this one? What's the probability of a club? 1/4, and I'm going to write it as 13 over 52 because when we add these together, we're going to want a common denominator. What's the probability of a face card? Well, how many face cards in each suit? We have king, queen, jack in each suit. We have 4 of those. So we get 12 over 52. We could reduce that if we want, but we're going to add the common denominators. What's the probability of a club and a face? How many of the face cards are clubs? 3, right? We have a king of clubs, queen of clubs, jack of clubs. So our probability of a club or a face is we add the individual probabilities, 13 over 52 plus 12 over 52. But these count parts of the overlap. So we're going to subtract the overlapping probability minus 3 over 52. And we get 22 over 52. 13 plus 12 minus 3 is 22. And we can reduce that. So that would be 11 26ths. So we have an overlapping probability. We have to subtract out the overlap. We're good with that example. Okay, let's look at another one. We're rolling 2 die. Two dice. I guess you can say dice. We want the probability of more than 10. So at first this sounds kind of complicated. But what's another way we can say we want to roll more than 10 on 2 dice? We're going to roll, what are our 2 possibilities for more than 10 on 2 dice? Just the totals. 11 or 12. So the other way that we can think of this probability of more than 10 is the probability of rolling 11 or 12. Do those 2 events overlap? Can we roll an 11 and a 12 somehow at the same time? No. So those are mutually exclusive. So we just have a nice mutually exclusive probability, 11 or 12. The probability of rolling an 11. How many ways can we roll an 11? 2, 5 and 6, or 6 and 5? Probability of a 12. How many ways can we roll a 12 on 2 dice? 1, just a 6 and a 6, right? So the probability of 11 or 12 is I wrote my denominators wrong, didn't I? Those should be 36s. Not adding, multiplying. So we get 3 over 36, which is 1 over 12. I was thinking of the result too early. All right, there's another way that we can combine probabilities. And that is if we have independent events. Independent events are ones where one doesn't change the other. So if you flip a coin and you roll a die, the one doesn't affect the other. What happens on the coin doesn't affect what happens on the dice. But if you draw a ball out of an urn and don't put it back, that does affect the probability of the next thing. When we have independent events, we say the probability of A and B, probability of both happening. When we have independent events, we multiply. So I think of this, when you have an and probability, means you multiply. Or means add, and means multiply. So for example, we flip a coin 3 times. We want the probability of all heads. So when you flip a coin, does one flip change what happens on the next one? If you flip 10 heads in a row, does that somehow make it more likely that the next one's going to be a tail? No, they're completely independent. The one doesn't change the other. So these are independent. And that's an easy mistake to make when you're talking about probability. It's like, well, it's got to come up heads next. It's got to. Each one is independent. In fact, on average, does anyone know on average how many times you have to flip a coin for the distribution to be about 50-50 heads and tails? About 100 for it to be a nice 50-50 distribution of heads and tails. All right, so a probability of all heads. Well, what's the probability of the head on the first flip? 1/2. On the second one, 1/2. On the third, 1/2. We have 1 in 8 chance of getting all heads. All right, questions about independent events? Okay, the last thing we need to talk about today is the complement of an event. So I'm going to say A is an event. We write A prime is the complement. And A prime is everything other than A. So if you're talking about, for example, flipping a coin, the complement of flipping a heads is a tails. That's the complement. That's the other possibility. And the probability of an event plus the probability of its complement. So the probability of something, one particular thing happening, and the probability of all the other things that could possibly happening, what would those have to add up to? 1. Or we can rearrange this. We can say the probability of the complement of an event is 1 minus the probability of an event. And this is useful because sometimes it's easier to calculate the probability of a complement than it is to calculate the probability of an event. And then you can use this relationship to find the probability of the thing you're interested in. For example, we're rolling 2 dice. We want the probability of the total of being less than or equal to 10. So one way we could calculate this, we could think of this as, well, that's the probability of getting a 1 or a 2 or a 3 or a 5 or a 6 or a 7 or an 8 or a 9 or a 10. And you could add those all together. So that's a lot of work. And depending on the event that you're talking about, it could be a huge amount of work to try to figure that out. What is the complement of less than or equal to 10? What's the other possible outcomes that are not less than or equal to 10? Complement of less than or equal to 10 is getting 11 or 12. Well, didn't we just calculate that? The probability of 11 or 12 we did in our previous example was 1 in 12. That's the complement of the probability of getting less than or equal to 10. So the probability of less than or equal to 10 is 1 minus 1/12. That's everything else that can happen. So 12/12 minus 1/12 is 11/12. And you would get the same answer if you found the probability of a 1 or a 2 or a 3 or a 4 or 5 or 6 or 7 or 8 or 9 or 10 and added them all together. But this is way easier. So sometimes it's easier to calculate the probability of a complement. All right, questions? Okay. Not example. This is homework. All right, there we go.